Hey class, welcome to another stats video. We've got a couple of ideas I'm going to present to you guys today. The first I kind of talked about last time, just kind of tangentially, when Quinn was asking why the heck do we have to use these rules for expected value and standard deviation. Hopefully after playing around with those rules last time, you can kind of see why they're useful for standard deviation. They're really going to help when we work with normal models. Random variables that follow normal models, to be more specific. All right, let's check out this first example, see what we can make of it, and honestly have fun with this. I think this is a cool problem. A company that manufactures and ships small stereo systems has packing times for each stereo system that follow a normal model with means of a mean of 9 minutes and a standard deviation of 1.5 minutes. The times for the boxing stage, a separate part of the packing process, or the shipping process rather, can also be described as normal with a mean of 6 minutes and a standard deviation of 1 minute. First question we're asked is, what is the probability that packing 2 consecutive systems takes over 20 minutes? Oh, and there's the message again that I really need to deal with somehow. Keep the current color scheme. Let's go with that. All right, what I want to start with is by drawing the normal model. It's been a while since we've done this. We're going to do this more second semester actually than we did the first. So we are told that the packing time for each box, let's label this. I kind of didn't give myself a lot of room for title, but whatever. Packing time in minutes follows the normal model, they said, with a mean of 9 minutes and standard deviation of 1.5. So to either side, we're looking at 10.5, or 7.5 minutes. Further down we get 6 minutes. This is at 2 standard deviations from the mean, or 12 minutes. Again, remember the 68, 95, 99.7 rule. So the 68% of the packing times for all boxes should fall between 7.5 and 10.5. 95% of the packing times for all boxes should fall between 6 minutes and 12 minutes. Okay, so that's one of the 2 pieces of information given to us. That's going to help us out. Second thing that we are given here is the normal model for the boxing stage. So let's just go ahead and start with the labels so I don't run out of room. Boxing time, also in minutes. Let's draw this out. We've got a bell curve, a little fatter. It's got some hips to it compared to the other one. We've got a mean of 6 minutes, a standard deviation of 1, so it's either side. We're looking at 7 minutes, or 5, 4, and 8 beyond that. And there you go. Okay, so again, 65% of all boxing times for these stereo systems should fall between 5 and 7 minutes. 95% of all boxing times for these stereo systems should fall between 4 and 8 minutes. Hopefully that makes sense. All right, so let's use that to answer A here. And A, they want the probability that packing 2 consecutive systems takes over 20 minutes. So we're talking exclusively about this red bell curve here for these 2 stereo systems. All right, let's define our variables. So the one thing that it's kind of our first trial. The first stereo system takes some number of minutes, right? So P1 is equal to the packing time for the first system. And P2 is equal to the packing time for the second system. Okay, one of the things that's great about random variables that follow normal models is that as long as your variables are independent, a combination of these variables, in this case a combination of P1 and P2, also follows a normal model. That's key. So if I say that T is equal to the total time to pack, not S systems, 2 systems, then T will also follow a normal model. And that's the normal model we don't have yet, that we need to answer this question. And to get that, we know that final equation we're going to set up here that's kind of new. T, therefore, must be equal to P1 plus P2. That's key. We are relating the P's, the variables for which we have a normal model. That's both of those packing times, P1 and P2, both follow the red normal model. T, we don't have a normal model for, and we're going to get that to answer the question. So, normal model has two parameters, remember. These red and blue normal models, the parameters were given to you already of mean and standard deviation. So we need the mean, we need the expected value of T. We need the expected value of the total time to pack these two stereos. Well, we know the expected value of T is the expected value of P1 plus P2. It's the sum of the first packing time plus the second packing time. Well, using our normal model rules here, we know that that's, the expected value rules, we know that's equal to the expected value of P1 plus the expected value of P2, no sweat, which both of those, either packing time has a mean of 9. So that's 9 plus 9, or 18 minutes. There's the mean for this new normal model that we're going to make. And then also, let's find the variance, which will give us the standard deviation. So the variance of T is equal to the variance of P1 plus P2. The variance and the total packing time for two systems is equal to the variance of the first packing time plus the second. And we can break that apart as follows using our variance rules for random variables. Variance of P1 plus the variance of P2 is equal to, well, note in red here for this standard, or for this normal bell curve, they did not give us the variance of the packing time for one stereo system. They gave us a standard deviation of 1.5. Remember, standard deviation is just the square root of variance. So if we want to find the variance from the standard deviation, you square the standard deviation you're given. So that's equal to 1.5 squared plus 1.5 squared, which is in turn, simplify that out and you get 4.50. 1.5 on it squared on its own is 2.25. So, semicolon here, standard deviation of the packing time of the first and the second has to be the square root of that 4.50, or 2.12 minutes. Okay. Now I told you this new random variable T would follow a normal model, and we just found the expected value and the standard deviation for that. Or excuse me, the mean and standard deviation for that. So our new normal bell curve looks as follows. We have, let's just draw this right in the middle. We've got our bell curve. We found a mean packing time for both boxes of 18 minutes. Standard deviation of 2.12. So off to either side. Check my math here. I think I'm right, but I'm not. I haven't double checked this. 20.12 and 15.18. Adding and subtracting the 2.12 that we found right here to either side. So that's the, again, leave myself room for a title. Let's add that. Packing times for two stereos in minutes. And there you go. Okay, now we can answer this question. Let's back up and double check that we know what we were asked to find. We were asked to find the probability that packing two consecutive systems takes over 20 minutes. So using this normal bell curve, we want to find everything right through here. Let's say 20 is right in there. We want to find all the sets of two stereos that take 20 minutes or more to pack. So to answer that, we need a z-score. There we go. We find the z-score by saying, well, 20 minutes is the data value we care about. Subtract from that the mean of 18. Divide through the standard deviation of 2.12. So our z-score is equal to 0.94. So rounding this up, we are almost finished. The probability that the total packing time for two systems is 20 minutes or greater. And we can put greater than or equal to there if we want. That's equal to the probability that we are 0.94 standard deviations from the mean or greater, and plug this into normal CDF if you remember on your calculator, and you will find that that percentage is 17.36. Or 0.1736 is the probability that the packing time for two stereo systems would take 20 minutes or over. And there you go. We have answered A. So let me cross that off the list for us so we can see that we're not going to use that as we go. Okay, separate question here. We're actually going to set up a second normal model for this. What percentage of the stereo systems take longer to pack than to box? Okay, so they're talking about packing and boxing both. We're actually going to rely on both the red normal model and the blue normal model that you see in this picture here. We're talking about two different types of variables now. So okay, let's come down here. I know it took a lot of space for A. Again, I think these are interesting problems, but they do take time. So in B, we're being asked to find difference in, or excuse me, let me back up and explain the logic here. So if we've got two variables here, let's call the first one P for the packing time and B for the boxing time. If we want to know what percentage of the stereo systems take longer to pack than to box, we really want to find when the difference between those two variables is greater than 0. That is to say, we care about when is P minus B greater than or equal to 0, right? We want to know when P is greater than B. So let's go ahead. That's the logic that we're going to use for this problem. Let's go down here and define our variables. So P is equal to the time to pack a system, a stereo system. That's the first thing we need. We also need B. That's equal to the time to box a system. All right? And the thing we care about, using that logic I just identified for you, we care about the difference between the two. We're going to let capital D be the difference in time to pack versus box a stereo system. All right? So D is equal to time to pack a box minus the time to box a box. Stereo system, rather. Okay, so we again need to find if we know that P and B both of these guys here follow their own normal bell curves, the red and the blue up here, then we know, because these variables are independent, packing time should not affect boxing time, and vice versa. Because these variables are independent, so too is D going to follow a normal model. So again, we need the two parameters for D's normal model. We don't have its normal model yet, but we can find them using our random variable rules. So we can say the expected value of this difference is equal to, well, we can make a substitution from this, the expected value of P minus B, which is equal to the expected value of P minus the expected value of B. This is one of those times when the rules are maybe a little bit silly, like Quinn had identified for us, but at least we're writing it out and we can see why the expected value comes out the way that it does. So the expected value for a packing time, or the mean of one packing time for a box, we see is 9 from that first red bell curve. So 9 minus the expected value, or the mean of a boxing time, is 6. So 9 minus 6 equals 3. We've got the first parameter that we need. May as well circle that. We've got the first parameter we need for this new bell curve for random variable D. Okay, now the harder of the two to find, obviously, is the variance, or the standard deviation, rather. We need to go through the variance to find that. So the variance of this difference is equal to the variance of P minus B. Again, just making a substitution there from the equation we have above, which, again, interestingly, the variance rule says that if you've got a combination of two random variables, it's just the sum of those two individual variances. So the variance of the packing time plus the variance of the boxing time here. Well, as you might remember, we've seen this quite a few times. The variances were not given to us. Standard deviations were. Standard deviation for packing time was 1.5. Standard deviation for boxing time was 1. So coming back down here, we're going to say 1.5 squared to get the variance of the packing time plus 1 squared to get the variance of the boxing time is equal to, let's come right over here, 3.25. Again, semicolon, so that must mean the standard deviation of this difference, or of P minus B, is equal to 1.80 minutes. Oh, and let's not forget the units here. 3 minutes is the mean time in this difference. Okay, so we've got the two parameters we need for our new normal bell curve. So let's write that bell curve out. Looks something like this, with a mean of 3. So right down the middle, we're going to draw our 3. We'll label, again, concisely here, because I do an awesome job of not leaving room. Difference in packing and boxing times for this bell curve. Okay, so mean and the difference is 3 minutes. Standard deviation off to one side is 4.80 or 1.20. Let's go 2 out for this. Negative 0.60 and 6.60. Okay, what does this 3 mean? I think it's a good time to pause and explain what this bell curve means, because I can't say that it's intuitive for everybody. All right, so if our mean is 3, that means that coming right up here, that's talking about the difference being 3. So it would take, that is to say, it would take exactly 3 more minutes to pack than it would to box, right? So how about this guy down here, this negative 0.60? Well, that would actually mean that B had been bigger. That is to say that the boxing time for this stereo system was greater than the packing time. And it took 3/5 of a minute more, that is 0.60, 3/5 of a minute more to box than to pack. So hopefully the normal bell curve that we're using here in green kind of makes a little bit more sense from it. All right, again, let's make sure that we know what we're being asked to find. We've got this green bell curve, that's great, but unless we know how we're going to use it, we're not done with the problem. What percentage of the stereo systems take longer to pack than to box? So, longer to pack than to box, that means that P has got to be greater than B. Our packing time has got to be greater than our boxing time. If this green bell curve represents the difference between the two, then we are looking to find when we have a difference of 0 or more. So we want all of this area for our normal bell curve in here. Does that make sense? So that's any time that the packing time is greater than the boxing time. So, okay, we're again going to use a z-score here. So rounding this problem up in blue, I'm not really color coding like I'm meaning to do, but I hope you follow along with what's going on. Our z-score is equal to not the variable, the data value we care about, which is 0, minus the mean of 3 over our standard deviation, which we found to be 1.8. So our z-score is negative 1.67. So the probability that the difference between these times is greater than 0 or greater than or equal to, we can use those interchangeably, is equal to the probability that our z-score is greater than or equal to, that is to say the probability that we are so many standard deviations greater than or equal to negative 1.67. Again, use normal CDF to find that probability. That percent under the curve is 0.9525. And there you go. We have answered B. Which, just double check with me real quick. Let's check to see that that answer makes sense, the 0.9525. We know that in one standard deviation of the mean, that's 68% of the data values. We know that within 2 standard deviations of the mean, that's 95% of the data values. On the left side, we're not quite to 2 standard deviations over, but to the right, we're including data values past that second standard deviation because it's everything going out here as well. So our answer looks to make a little bit of sense. And you're welcome to check to see if it looks good. I think it does. All right, so there you go. Let me recap for you what we did. We identified random variables that followed a normal model and then used a combination of those variables to get, in turn, a new normal variable. We did that twice. In Part A, our normal variable represented 2 consecutive packing times. In Part B, it was the difference between a packing time and boxing time for a single stereo system. And that is fair to do, again, as long as your variables are independent. If the packing time forced the boxing time to be a little bit different, based upon how long the packing time was, this would not have been legit. So for you to be able to use this method, you first need to check that the variables we're talking about are independent. And there you go. I think it's a cool problem. Hope you enjoyed it. All right. New type of thing here. We're going to start Chapter 17. Chapter 17 has us working with special probability models. Okay, so let me see if I can speed this up a little while. I imagine I took a fair amount of time. Suppose a computer manufacturer rejects 3% of the chips produced because they failed pre-sale testing. We want the probability that the third chip you test is the first bad one you find. Okay, what we are talking about, we're going to call these trials Bernoulli trials, after the famous mathematician who designed the geometric probability model that we're going to be working with today. Bernoulli trials always come in the following form. Your outcomes are one of 2 things. Only ever one of 2 things. In this case, if we are pulling computer chips, I assume it's like a processor, if we're pulling computer processors from the manufacturing line, one of 2 outcomes can occur. We can either have a chip that fails its pre-testing, or pre-sale testing rather, or we could have a chip that does not fail its pre-sale testing. Only one of those 2 outcomes can occur. And to use the geometric model, which you're going to see on this slide, you've got to know that your trials, your random events, can occur one of 2 ways, not more, not less. Obviously not less. A random trial with only 1 outcome isn't random. Okay, so I want to introduce this by saying the following. Let's say that with these Bernoulli trials, in Part A here, the probability of success for any one chip that we pull, we're going to represent that with lowercase p, is equal to 0.03, because we want the probability that the third chip you test is the first bad one you find. So our success in this case is finding a bad chip. And we know that finding a bad chip has a 3% chance of occurring for any given chip. Okay, so the probability of success, even though it's a bad chip we're looking for, is 0.03. Probability of failure would then be the complement of that, because there are only 2 events happening, 97%. All right, I can painstakingly, and I'm going to do that here one time and then not after that, because it's painstaking. I can represent this problem with a binomial tree. So on the first draw of a chip from the manufacturing line, it is either good or it is bad. If it's good, it occurred with a 97% chance of probability. If it's bad, we actually don't care about that. So I'm just going to do a little fuzzy thing here, because that's not really what we want in the problem. We want the probability that the third chip you test is the first bad one you find. So we don't care if the bad shows up on the first trial. Okay, so there's your first trial. We had a good one. Second trial, we either have a good or a bad chip, right? Similar to the first. These are independent events. You are, and this is where it gets a little bit sticky, you are supposed to infer from the description of the problem that these are independent events. In general, if it would make sense to infer that there are independence between your trials, I keep saying events, I mean to say trials. If there are independent trials here, then you need to infer, let me back up, that did not make sense. If you have a series of trials, infer independence between those trials as long as it makes sense. That's what I'm trying to say. So let me explain why we could assume independence. In a manufacturing line, defects occur in a random in a random way. Obviously, manufacturing is not a perfect science. It's not dealing with equations. We're making stuff, and stuff doesn't always work out on the manufacturing line as you would expect it to. Having one failed computer chip doesn't automatically mean the next one's going to be a failure. It could be, it could not be. So, independent trials here. Sorry that was convoluted. Hope that makes a little bit of sense right now. Alright, so second trial, we either have a good or a bad chip. If we have a good chip, that occurs with a probability of 0.9409. That is 0.97 squared because these are independent trials. The probability of success or failure for this first chip doesn't influence the probability of having a good or bad chip on the second. Bad we again don't care about because we want to know just the probability that the third chip you test is the first bad one you find. So, okay. Last series of tree limbs here, we either get a good or a bad chip in the third draw from the manufacturing line. If it's a good chip, that is 0.97 to the third power. We found a good, we found a good, we found a good. So 0.8853. If it's a bad chip, that is 0.9409, which we just found, times probability of success. That is that we finally found a chip that didn't work, 0.0274. All right. I filled in the wrong numbers there. My mistake. Not 0.8853. That should be 0.9127 and 0.0282. Okay. Note that this, let's do this in blue because we're building to a big idea. Note that this 0.0282 has been 2 failures followed by a success. Yeah, that's right. 2 failures followed by a success. That looks good. To get us to the event that we cared about, that the third chip you test is the first bad one you find. If we had extended this and we were instead asked, what's the probability that the fourth chip you test is the first bad one you find? Okay, let's draw one final series of limbs here for good and for bad. We would have 0.8853 multiplying again just the 0.9127 times 0.97 and 0.0274 to find the probability that we found a bad chip on the fourth draw. That, note, is 3 failures. We found 3 good chips followed by 1 success. We found a bad chip on the assembly line. So, in general, if you have, we're going to continue with blue because this is big idea stuff. In general, if you have Bernoulli trials, your geometric model is represented as follows. Every time, please write this. P is equal to the probability of a success. Q is equal to the probability of a failure. And capital X is represented as the number of trials until a success in our Bernoulli trials. So up here, just let's connect that. So X, the random variable X, was equal to 3 in the first case. In the second blue case, random variable X was equal to 4. So we had 2 failures here and here before a success in the third case. And then in the second example, we had 1, 2, 3 failures before a success right here. All right. So if X is the number of trials until a success, then this is the equation that we need, right, as follows. The probability that a random variable X that follows Bernoulli trials, success or failure, one of 2 outcomes on every trial, equals sum X. That could equal 1, it could equal 2, equal 3. The lowercase x is which trial you finally find your success on. That is equal to Q, the number of failures, to the X minus 1. If you find your first success on the 5th trial, you have failed 4 times, hence x minus 1 times p. And that last trial, you finally find your success. 2 parameters for this model. I think parameters like the normal bell curve, these 2 things are important. The mean for the geometric model is always 1 divided by the probability of success. The standard deviation, sigma, is equal to the square root of q over p squared. These are derived in your book. I don't really want to take the time to do this. I think after the conversation we had last time, that's not a particularly fruitful way to go. However, everything in this box you need to know not only for my test coming up in probably a week's time, maybe just over, but also for the AP exam, your formula sheet, your reference sheet doesn't have those things on it. You're expected to have those memorized. So important to know. All right, so we actually found the probability that the 3rd chip you test is the first bad one you found a while ago right here. Let's go ahead and answer part B. Let's go ahead and answer part B, the probability you find a bad one within the first 12 you examine. Oh, let's change this. What's the probability that you find your first bad? Your first bad one on the 12th that you examine. Does that make sense? So we're finding the first bad one on the 12th chip that we're drawing from the manufacturing line. Okay, so part B, we can just say, well, that's the probability. We know that we follow a geometric model here because we have Bernoulli trials. You either find a bad chip or you find a good chip. Probability that x, the number of chips you draw from the assembly line before you draw a bad one, is equal to, or until you find the bad one, the probability that x is equal to 12 is equal to 0.97 to the 11th power. We find 11 good chips, and then we find the bad one with a 3% probability there at the end. That's equal to 0.0215. And there you go. That saved a ton of work in red, knowing this geometric model that we have boxed in blue. All right, we are almost done. Last problem does not take as long. So you guys have been patient, you've done great. Sorry if I'm running over time. On average, how many donors must be checked to find someone with type AB blood if only 4% of people have type AB blood? All right, well, part A, we can answer that quickly now. We have the probability of success is 0.04. Oh, and let's back up. Obviously, we have Bernoulli trials here. You either have type AB blood or you do not have type AB blood. So the probability of failure is equal to 0.96, and we're going to let capital X be the number of donors checked before, or until, I shouldn't say before, I should say until finding someone with type AB blood. All right, now I should mention here while I'm thinking of it, should you guys be defining your variables? Absolutely. Absolutely you should be defining your variables. And when you're working with Bernoulli trials, you need to be telling me P and Q as well. You guys have, for quite a while, tried to do things in your head as best you can, and you guys have done a pretty good job with probability trees. I've seen those written out like crazy. Please, please, please define your variables. We've got so many to keep track of in this unit that is, I swear it's going to help you out. And you will get more partial credit on a quiz or a test if you're telling me what you're defining or what variable you're trying to use through your definition, if that makes sense. All right, so we've got everything set up. We want the average number of donors that must be checked until we find someone with type AB blood. So we want the expected value of the random variable we just found, which we know follows a geometric model. So that's just equal to 1 over p. That's what I showed you in the blue box last time. which is 1 over 0.04, which is 25. So 25 donors we expect to check on average until, or that's the 25th donors when we would expect to see the first person with type AB blood on average. So A is knocked out, not too bad. B, what's the probability there's a type AB donor among the first 5 people checked? All right, so we want in part B, we're not going to redefine X. We've already got the variable that we need. We want the probability that we have someone, the first person that we encounter, that we interview here, or, what's the term I'm looking for? The first person whose blood we draw has type AB, or that the second does, or that the third, or that the fourth is the first person to have type AB, or that the fifth person is the fifth person is the first person to have type AB blood. So these are disjoint events. You cannot have the first person have type AB blood and the second person whose blood you draw also be the first person to have type AB blood. So because these are disjoint events, for all these U symbols, remember we can just add those separate probabilities. So this is equal to the probability that we find success on the first person, P, plus the probability we find failure then success, plus the probability we find 2 failures, 2 people without AB blood, then a success, plus Q to the third P, plus, Q to the fourth P. Substitute in your Q's and P's that we wrote out above. You have 0.04 plus 0.96 times 0.04 plus 0.96 squared times 0.04 plus 0.96 to the third times 0.04 plus 0.96 to the fourth times 0.04. All of that is equal to 0.185 in the box. And there you go. That's the probability that we would find a success among the first 5. 5 separate things added up together. So we've knocked out B. C actually is almost the exact same problem, only with an additional use of the geometric model. Instead of this that we wrote out right here, we would just add at the tail end right here 5 failures then a success to find the probability that the first type AB donor will be found among the first 6 people. So I'm going to skip that because it's almost identical to B. D here, what's the probability that we won't find a type AB donor before the 10th person? Well, I don't want to write out a probability tree. Hopefully you can visualize this with me here. To get a success, that means we would have a success. We'd find our first person with type AB blood on the 10th, 11th, 12th, 13th, 14th, 15th, 16th, etc., on and on and on and on person, all the way up down the line. To get any one of those outcomes, we have to fail how many times? 9. We have to fail 9 times. We cannot find someone in the first 9 draws from this group of people. So to wind up D and to wind up your notes here, the probability that X is greater than or equal to 10 has to be the same probability that we would fail in finding someone with type AB blood 9 times, which is 0.96 to the 9th, which is 693. I'll flex that up. And there you go. So big things from this lesson. Combining, let's cross out that we did need. Combining random variables that follow the normal model also gives you a new normal model. And then the second thing we looked at was the geometric model. And there you go. Let me close this out, and I'll see you guys later.